Hi guys, my name is Carlos Nesteria, and today I'm going to be creating a two-dimensional wind tunnel in Ansys Fluent. This is for project 1, and this is for design of aerospace experiments. So we're given the settling chamber height is 22 inches, the length is 15 inches, contraction chamber length is 24 inches, contraction ratio is 9, test section length is 12 inches, width and height 6 inches, diffuser length is 42 inches, half diffuser angle is 3 degrees, and the area ratio is 3. So let's go ahead and open up our workbench in Fluent. So as you can see, we have it open. We're going to select Fluid, Flow, Fluent. We're going to right-click Geometry. We're going to open up a Design Modeler. I've already opened it up to save time. So we're going to select XY plane, Z plane. We're going to create a line. We're going to zoom this in actually. 1v2. There we go. Create a line like that. We're going to create another line as so. Contraction chamber, and settling chamber, and then we're going to create our diffuser section. We're going to move this here. Oh, messed that up. If I can do that. There you go. So this is the rough sketch of the wind tunnel. Now we're going to go ahead and add dimensions so that it looks nice and neat. Let's set the horizontal dimensions first. So it says here that the settling chamber has to have a length of 15 inches. So 0.381 meters. It's the same thing for this part. 0.31. This is some vertical dimensions. So the settling chamber is a height of 22 inches. So 11. I'll go ahead and do this. Sweet. Now we have that. We're going to go ahead and set horizontal dimensions for the contraction chamber. Contraction chamber has to have a length of 24 inches. 24 inches is 0.6096 meters. 0.6096. It's the same for this here. 0.6096. All right, sweet. So now that we have that, let me go ahead and fix this here. Something's not right here. This line right here is not. Delete that. Four. Select sketches. Actually, it's fine. Once I fix this, it'll change. So dimensions, let's do vertical. So for the test section, height has to be 6 inches. So 3. Same thing for this part here. So V8. Yeah, I have to go back and fix this. So we're gonna go ahead and click this here. We're gonna delete this line. Delete this line here. We're gonna select sketch line. And then there we go. Back to dimensions. Horizontal dimension. It should be H1, 0.3 H1. So H9 is perfect. These heights are good. Oh, let me select this right here. It's V10. V10 should be V9 or V8. Yours the same. Okay, so now we're gonna set this length here. Yeah, 0.6. Yeah, I guess I could have fixed it this way too, but I guess both ways work, doesn't matter. So now that we have this part squared away, this is perfect here. Now we're gonna go ahead and do the test section and the diffuser. Let's do horizontal dimension, select here, horizontal. Select these 2 points here. So the test section actually has to be 12 inches in length. So this part here, page 13, 0.3048. Okay. Diffuser has to be 42 inches. Okay, sweet. Now that we got that done, we're gonna go ahead and set the angle, the half diffuser angle. Set the alternate angle. Not sure why it does that. So A16 should be 3 degrees. Oh, it doesn't do that. Angle 18 should be 3 degrees. All right, sweet. So now we have all the dimensions set for our wind tunnel. This is what it should look like. Let's go ahead and delete this line here. We're not gonna need it anymore. Okay, perfect. So now that we have done this, we're gonna go ahead and create code of concept, surfaces from sketch. We're gonna just hold all these together, apply that, and then hit generate. We're gonna create a surface. Now we can go ahead and mesh this. So let's go ahead and go back to our workbench. Go to mesh. Let's reread that. Let's get it's open. Give it a second. Okay, cool. So now that we have that, then let's open there. Let's insert a method. Let's delete this too. So for method, we're gonna select that, apply that. We're gonna do triangles. And here we're gonna select that. So yeah, it's good. And then we're gonna hit generate. Meshing right now. There we go, perfect. So now we have our mesh. Now we're gonna go ahead and select the boundary names. So select this as the top of the wind tunnel. Wind tunnel walls. Let's go ahead and do that. Settling chamber inlet. Let's do this one here as diffuser out. Okay, perfect. So now we have that. We have these three names where you can go ahead and close that. Let's go update that. There we go. Now let's go to setup. Position. Okay, let's go start. It's going to open up. Give it a second. Okay, so there we have our mesh design. So first things first, let's go to setup, general, pressure base, it's fine. Full screen. Okay, cool. Energy, let's turn energy on. Viscous. It's a kale. Nicholson, epsilon. Materials fluid. Let's make sure that's good. It should be 1.225. There we go. That's for the density. Close that. Boundary conditions inlet, settling chamber inlet. Now we're gonna do actually have velocities written down. Test report. So let's do a velocity in 0.55 meters per second. That gives us a test section velocity of 2.12 meters per second, which is for the 10 hertz. So let's do 0.55 meters per second. There we go. Apply that, close that. Internal. Oh, I actually forgot to turn on. Let's go to models again. Materials. Close that. Boundary conditions. Okay. That's good. The global is fine. Named expressions. That's good. Controls. Good. We're not going to initialize it yet. Enhanced wall treatment. I'm not sure why it's not. Maybe. Okay, it's all good. So yeah, we're gonna have the enhanced wall treatment, pressure gradient effects too, and we should be good. Perfect. Enhanced wall treatment, pressure gradient effects, and hit. There you go. So now that's done. We're gonna go ahead and initialize that. Initialization. Initialize. It's done. Now, what we're going to do now is we're going to create, let's see, so run calculation. Really, it only takes like 120 iterations, but let's do, we're going to set 800 case. Calculate that. It's running, it's going to converge. Oh, I guess it's taking more than 100 iterations. And I'm not sure why it's taking so long. I might have to go back and play with the settings in a second. Yeah, it shouldn't converge like this. For some reason, it's doing it. It's gonna end right here. Watch. Yeah, I'm not sure why I did that. Let's go to graphics, contours, just to select all of these. The velocity. Okay, that looks reasonable. So yeah, this is what we get if we run the velocity magnitudes. Let me go back and see why it took so long though, why it took so many iterations. What was it? Calculation activities. Because when I did it on my own, it only took like 120 iterations. Putting interval. I'm gonna have to go back and play with this a little bit and see why it's taking so long. But either way, we got the results we wanted. So as you can see, we have the velocity magnitude contour. Let's go ahead and let's edit that. Let's just set this velocity. Oh my God. I guess you can make that. That's fine. Velocity magnitude. Perfect. And this is what we get. So we're going to compute that, save and display. So our max is 2.12, which is at the test section, midsection. So that's perfect. Now let's go ahead and create the contour for our pressure. Let's do static pressure first. Set all of these, compute that, save and display. This is our static pressure. Now let's do a dynamic pressure, dynamic pressure, compute that and display that. As you can see is what we get. It's pretty reasonable. It's just the velocity. As the velocity increases, dynamic pressure is going to increase. As the velocity decreases, the dynamic pressure is going to decrease. So they're both hand in hand. You can see the dynamic pressure is highest here in this area because of Bernoulli's principle, and velocity increasing as it enters the test section. Let's go here. Let's edit this. It's static pressure. Static pressure. So, oh yeah, let's do one more for total pressure. Total pressure. And this is our total pressure. Okay, cool. So this is what we have. Now let's go ahead and do XY plots. So the XY plots are going to tell us specifically how it changes numerically. So first we got to create a new surface. Let's create a point. Oh, not a point. New surface line. So -1, 2, 5. This is going to be in meters. This is across. Create, close, cross. This is the velocity. There we go. Perfect. Save plot, close. This is what we get. Perfect. This is going to be the velocity across the wind tunnel. So as you can see, the velocity starts off pretty constant here, and then it starts to increase as it goes through the contraction chamber. It levels off in the test section and starts to decrease again as it leaves the test section and it enters the diffuser. Now let's go ahead and create one for our pressures. Let's do static pressure. Let's select cross here. Static pressure. This is what we get for static pressure. It starts with atmospheric pressure and then it decreases and then it increases again as expected because it decreases as velocity increases in the contraction chamber. The pressure is going to decrease inversely, and it's going to increase in the diffuser section as velocity decreases in the diffuser section. So let's go ahead and see what we have now for dynamic pressure. Across certain plots. Oh, did we not plot it? Dynamic pressure across saved plots. Close. I'm not sure what happened. Dynamic. I don't know what's going on with this, to be honest. Pressure, dynamic pressure across. Yeah, I'm not sure why it's not plotting it. It's kind of weird. Let's see, because it did it for the contour. We haven't done it. Yeah, we got this. Let's go to plots. So total pressure. Let's see what happens with that one. Maybe just take it a while. Oh, there we go. I'm not sure why it wasn't working for some reason. So yeah, dynamic pressure, perfect. And let's do total pressure across. There you go. So this is what we're getting for our XY. So it's dynamic total pressure. Perfect. So we have velocity, static pressure, total pressure, dynamic pressure, and total pressure. Right? Yeah, perfect. So yeah, reports. Again, one way I found the test section velocity was I created a report, and I can show you how to do this actually. So if you want to be really specific, let's look at the velocity contour. Okay. If you want to be really specific and create a point, and then 0.6, you just say origin, and then you can set this to 0, 0, create, and then when you run a report, we're going to select surface integrals. We're going to select origin. We're going to select vertex maximum for velocity, and then we get 1.92, which is really close to the 2.1 that. And this is magnitude. This is let's see, vertex average. Yeah, it's very close to what it's 2.1. And that's at the origin, but actually, yeah, so this is at the origin, which is like right here. But in the project, it asked for the velocity right in the middle of the test section. So it'll be 6 inches. So let's go ahead and calculate that. So 0.1524. Let's create another point, and it's going to be the mid section. So 0.1524, and then perfect. So now our point's right in the middle, and then we run that midsection right here, compute. We are very close, very, very close. 2.07, and that's how I found. I played around with this and our inlet velocity and found the exact number for the inlet velocity that would match the 10 hertz frequency of the project. So now that we have this, it also wants us to find the, so we did this. Now it wants us to find the vertical velocity, static pressure, dynamic pressure. So the way I did this was I went here, I went to the XY plots, same way, but instead of creating, so we're going to set this to 0, 1, because we're going in the vertical direction. That's fine. Let's do velocity. Now let's create a new line, and the line is going to be 0, 0. This time we're going to go from, let me reference my project report so I don't have to calculate the distance again. So from negative 0.08 to 0.08. So negative 0.08 to 0.08. And then we're going to say vertical, create that, close that, vertical, and then save plots. And then we get this. So this is our velocity. And it makes sense too, because right here where you get these 2 dots, that's the no slip condition. At the edges, at the top and bottom of the test section, not going to have any velocity because of the adhesion to the surface. It's going to be no slip condition. But as you can see, the velocity profile changes across the center line. So that's for the velocity. Let's do the pressures. Let's do static pressure. Let's do vertical. Let's do 0. Let's do 1. Plots. Get this for our static pressure. 0. Let's do 1. Let's do dynamic pressure. And then let's set vertical. That's what we get. And then let's do total pressure. 0, 1. Vertical, close. Get this. So yes, this is how you create the wind tunnel in Fluent, guys. And Yes, this is the entire project. The last part is Excel. So it's asking for P inlet minus P exit. I used the point function and I found the pressure at the contraction inlet, contraction outlet, and then I also found the dynamic pressure, and then I plotted that in Excel, and got my calibration constant. Thank you.